In this session, we will try to understand the incompressible flow over flat plate. So let's say we have a flat plate, uh, and this is the x-axis, this is the y-axis over the flat plate on somewhere, and let's say we have a velocity v infinity going from this direction, that is the free stream velocity, and the boundary layer formation is something like this, and this is the velocity profile inside the boundary layer. This is the boundary layer thickness at distance at some distance of x, and at the boundary surface the velocity will be 99% of the free stream velocity. And if we talk about the gradient, any point if we are taking the gradient, that is del v upon del y, that can be denoted as this, because v here is a function of x and y, and because we are going from bottom to upward direction, that's why we have taken the gradient del v with respect to y. Okay, and the thing is that as we are moving upward, then at this point at the boundary surface, the del v upon del y is equal to what? Zero, because there is no change of the gradient at the boundary. So hydrodynamic boundary layer is a thin region formed over the flat plate inside which velocity gradients are seen in the normal direction to the plate. These velocity gradients are formed due to the viscous nature, or rather momentum diffusion through the fluid layer in the normal direction to the plate. Outside this hydrodynamic boundary layer, everywhere free stream velocity prevails, hence no velocity gradients appear. What does it mean? It means that the outside this boundary layer means this in these all these positions there is no component of the shear stresses. No velocity gradients are present. But inside boundary layer we have velocity gradients like this del v by del y or del v by del x, something like that. Let's clear it down. So let us try to find out some evaluate some equations, some try to understand the what are the boundaries. The boundary conditions of hydrodynamic boundary layer are at any given location of x measure from leading edge of the plate. If we want to find out, then try to understand in this figure that at y is equal to 0, if we want to find out the velocity v should be what? V should be 0. The vertical component of the velocity is 0 at y is equal to 0, because at y is equal to 0 there is a flat plate, and on the flat plate there is a no slip condition, and on the no slip condition there is not movement of the fluid particle. That's why horizontal component as well as the vertical component both will be 0. If we talk about the y is equal to delta at boundary layer thickness, then at that uh, location, that horizontal component q will be 99% of the free stream velocity. And as to y is equal to delta, del u upon del y is equal to 0. Velocity gradient is 0. I'm sorry, shown here, I have shown here what? U. But this will be what? This is u. Horizontal component of the velocity. Horizontal component of the velocity at location delta is horizontal component, not the gradient of horizontal component, that is u, is equal to 0 at delta location. So here it is very important to understand that why the horizontal component of the gradient is equal to 0 at delta location. Because we are seeing here that this is the what? This is what velocity. We are showing this the horizontal component of the velocity u, that u is continuously increasing till what? Till the boundary layer thickness, and at the boundary layer thickness there will be not any gradient of the velocity. Why? Because there is not the effect of the shear stresses. That's how we have defined the boundary layer thickness, that the the thickness at which the shear stresses are neglected. It means that there is no relative motion between the layers. All the layers will flow with the same direction. I mean that flow here is going with V infinity. There is no relative motion between the layers. It means that the gradient of the horizontal components of velocity above this point will be zero. That's why we have written that del u by del y is equal to zero. Fine, this understood. And at y is equal to zero, if I talk about y is equal to 0, at y is equal to 0, what if I want to find out del square u upon del y square, that will be 0. Let us try to understand that what does it mean? What does it mean actually? Uh, uh, Actually, we are doing del upon del y is equal to del u upon del y. We have taken here 0. So first try to understand that where it comes from. It comes from the shear stress. You know that shear stress is equal to mu del u by del y. Okay. If del u by del y is equal to 0, it means the shear stress is 0. Like this. Like this. Del u by del y is equal to 0, then shear stress is 0. As I have explained that at this point, the shear stress will be 0 because there is not effect of the shear stresses till the boundary layer. Outside the boundary layer, there is not any effect of the shear stress. That's why del u by del y is equal to 0. But at the location y is equal to 0, what is happening? At the location y is equal to 0, the shear stress is maximum. Shear stress is maximum and it is reducing continuously going upward direction. So if the shear stress is maximum at the y is equal to 0 location, then how you can find out the maximum shear stress? How you find the maximum of anything? For maximum of anything, we differentiate of that function. So if we differentiate tau, that is del uh, just, okay, del tau upon del y, that should be 0, and which result that del square u by del y square we have to find out 0. That's why we have written 0 here, because the shear stress tau is maximum here. You can write it like this. So we can say that tau is maximum. It means that del u upon del y is maximum at y is equal to 0. The velocity gradient is maximum here. Of course, that is maximum here, and it is reducing going upward direction and it becomes 0 at the boundary layer. Fine. So I'll define some more terms. Some more terms like local Reynolds number. At any location x, the Reynolds number will be defined like free stream velocity v x rho upon mu. X is the characteristic dimension till the location x. That's why it is defined the local Reynolds number. So that's how we can define the laminar and turbulent layers, laminar and turbulent situations in the flat plate. How when we say that the flow is laminar in case of flat plate, when the local Reynolds number x is less than 5 into 10 raised power 5, or we can say 5 lakhs. When local Reynolds number is less than 5 lakhs, then that is called laminar flow. What about turbulent? When local Reynolds number is greater than 65.2 7 into 10 raised power 5, it means that 6.5 lakhs to 7 lakhs, more than that, then that is called the terminal boundary layer. And in between that, the flow is called the transition flow. 6.5 usually be in case of the rough plate, and 7 lakhs for the case of the smooth plate. I mean, if the plate is smooth, then more than the 7 lakhs of the Reynolds number, local Reynolds number is assumed as the turbulent flow. If I show you the different flow regimes, then I can show like this: the boundary layer, then after that at some location x, when x increases, then Reynolds number increases, then it becomes some transition zone, then again, and then it becomes fully turbulent. So here it is laminar, after that here it is turbulent, and here the flow becomes somewhat eddy. Fine. Here you will get the velocity profile parabolic, and here you will get the turbulent velocity profile, that is logarithmic. Uh, if I have to show the turbulent region, then I can show it like this. Fine. Okay. Then there was a question asked in the gate. What was that question? That we have, let's say we have a cylinder and there is a flow over it. Till what point the flow will be laminar? Then the actually this is the boundary layer. Boundary layer will be something like that. So the thing is that experimentally it is observed that till 80-degree angle the flow becomes laminar. So till 80-degree angle the flow will become laminar, and after that it becomes transition, then finally becomes turbulent. This is the flow across cylinder. So for any given velocity with a given surface temperature of body, the local convecting heat transfer coefficient in the turbulent domain are always greater than those in the laminar region. More often, we come across laminar flows during forced convection heat transfer into our flat plate. So, for laminar flow over flat plate, the velocity distribution within the laminar hydrodynamic boundary layer can be given as, actually it is derived, so I'll directly write it. The velocity profile, what is we are getting that velocity profile for the case of laminar flow. So because it is following the parabolic profile, so we have a equation for that, that is written as u upon b infinity is equal to 3 divided by 2 y by delta minus half y by delta whole cube at any location x measured from leading edge of the plate. This is the velocity profile, where delta is the hydrodynamic boundary thickness. Delta is the hydrodynamic boundary thickness, or delta can be written as delta is equal to 5x upon square root of Rx. Thing we have to keep in mind that this horizontal component of the velocity is actually the cubic profile. It is the cubic profile. So here it is try to focus here that profile this profile is for what, this profile is for u, that is u, if you write with function of y, so it is following the cubic profile that is shown here. This should keep in mind. So further we'll try to understand some of the things, some physical significances. Let's say we have two boundary layers, boundary layer 1 here and boundary layer 2. So what is the difference between two? Here boundary layer thickness is delta 1, here boundary layer thickness is delta 2. So delta 1 is less than delta 2. What is the difference? Here we can say that in the first case, the momentum diffusion rate is very slow. Momentum diffusion is slow. That's why boundary layer is thin here. But in the case of the second, the momentum diffusion is faster. Momentum diffusion is faster. That's why boundary layer is thick here. Thus, a fluid having more kinetic viscosity nu will form a thicker hydrodynamic boundary layer over flat plate as compared to the fluid having lesser kinetic viscosity for a given free stream velocity. From the equation, like delta is equal to, we have written it 5x upon under root Rex. From this equation, we can also show that delta is equal to 5x upon divided by uh, uh, that is rho v x upon mu, or 5x divided by v x upon kinematic viscosity, or delta is directly proportional to square root of kinematic viscosity. So as the kinematic viscosity is more, delta will be more. The, the more viscous fluid will form more thick boundary layer. Fine. So one thing I also show from this equation that I'll directly show that if we have a boundary layer, and this is the velocity profile of u. So at the location y is equal to 0, the gradient del u upon del y at y is equal to 0 is what? Del u upon del y, whatever will be, it will be maximum because tau is maximum here. Shear stress is maximum here. So we will define this as tau wall, that is the local wall shear stress, local wall shear stress, and this will come out to be like mu del u upon del y at y is equal to 0. If we will derive, then we will get mu v infinity 3 by 2 delta. That is the tau wall. This much of Pascal shear stress we are getting at any location of x. So the wall shear stress physically indicates the frictional drag or the drag force exerted by the fluid on the flat plate. And from that delta equation, we can see that delta is directly proportional to square root of x. Square root of x. Like this profile is actually the parabolic profile. This is following root x profile. And if we'll talk about the shear stress tau, like we want to draw x versus tau and how the shear stress is changing with respect to x. So from this equation we are seeing that tau is inversely proportional to delta, and delta is directly proportional to root x. So tau is inversely proportional to root x. So it is actually following the this much. So shear stress is continuously decreasing as we are going towards the, as we are increasing the x, as we are moving forward throughout the plate, the shear stress is going to decrease. That's how the shear stress is changing. Now we'll try to understand. We have understood the concept of the Reynolds number, its significance. Now the next topic is the Nusselt number. Nusselt number, it is Nu. What is Nusselt number? So as we have derived from the dimensional analysis that Nusselt number is come out to be He upon K. But K is what? K is the uh, conduction heat transfer coefficient. But this conduction heat transfer coefficient is applicable here for the fluids because Nusselt number is defined for the case of the flow. Okay, if we'll manipulate some more, then we can write it like this: d upon Ka divided by 1 upon Ha. So what is d upon K? D upon K is thermal resistance. What is 1 upon Ha? That is also the thermal resistance. This is in solid in case of conduction, and this is in convection. So we can show that Nusselt number is the ratio of conduction thermal resistance offered by fluid if it is stationary divided by the surface convection resistance. This is the significance of the Nusselt number. So now if we want to approximate the Nusselt number, that what would be the Nusselt number around? So because Nusselt number is defined for the fluid, for the flowing fluid, and it is the ratio of the conduction thermal resistance toward the convection thermal resistance. So just think that there is a fluid flowing. So what will be the conduction thermal resistance? What is the conduction thermal resistance and what is the convection thermal resistance? Surface convection resistance. Surface convection resistance. So as we can easily try to get it that conduction thermal resistance is very low for the conductors. I mean, conduction is very fast for the conductors, so conduction resistance is very low for the conductors. But in the case of the fluids are not generally the conductors, so the conduction resistance is very low. Conduction resistance is very much for the case of the fluids as compared to the surface convection resistance, because fluid is just for defined. I mean, the convection is just only defined for the fluids, because fluid is more dominating for the convection. That's why surface convection resistance will be very less. Surface convection resistance will be less because the convection resistance is the convection is only defined for the fluids. And if I talk about the conduction thermal resistance, so conduction is defined for the solids. And if we talk about the resistance, so conduction resistance with respect to the fluid in the solid will be very less. But in the case of the solid, the conduction resistance will be more. So that's why we are getting here that the Nusselt number will be greater than 1, because the conduction resistance is more for the fluids. That's the funda. And one more thing we have to keep in mind that Nusselt number actually resembles with Biot number. Nusselt number is equal to Hg upon K fluid. Biot number is also written as Hs upon K solid. It sometimes resembles. And Biot number is actually defined as internal conduction resistance divided by external convection resistance. So be smart here. I mean, don't be confused with Biot number and Nusselt number. There is not any relation. Fine. And one more thing, that Nusselt number, we know that Nusselt number is usually greater than 1. And for the lumped heat analysis, the Biot number is taken as zero point 0.1. I will discuss further. Now the next number which we have got from the Buckingham pipe theorem, that is the Prandtl number. What is the Prandtl number? So Prandtl number, we have got that that comes out as mu Cp upon K. If we'll elaborate it more, then we can write it like that it is mu upon rho divided by K upon rho Cp, or we can write it as kinematic viscosity, and this is called thermal diffusivity alpha. So so Prandtl number is actually the ratio of kinematic viscosity to the thermal diffusivity. So it is actually tries to compare uh, between the kinematic viscosity or thermal diffusivity, that what is dominating, thermal diffusivity is dominating or the kinematic viscosity is dominating. So Prandtl number is the only dimensional number which is a property of the fluid, defines as the ratio between kinematic viscosity of the fluid and its thermal diffusivity. Let's say we have a fluid flowing over a plate. So if we talk about the thermal boundary layer, it will be like something like this. But what about the, I mean, that this is the hydrodynamic boundary layer. But what about the thermal boundary layer? If you want to plot the thermal boundary layer, then that will be here or here or here. That is decided by the Prandtl number. If Prandtl number is more than 1, it means that kinematic viscosity is more. It means that hydrodynamic boundary layer will be more. And if it is less than 1, means that Prandtl number is less. It means that thermal diffusivity is more dominating more. It means thermal boundary layer will be more. That's how Prandtl number decides. If we'll see some data, then for the case of the air, Prandtl number comes out as 0.63 to 0.71. It means that the Prandtl number is less than 1. It means that the thermal diffusivity is dominating in case of the air. If I'll draw, then if it is our thermal boundary layer, hydrodynamic boundary layer, in and if I want to draw the thermal boundary layer, thermal diffusivity is more here. It means thermal boundary layer will be this. thermal boundary layer. If I talk about the water, let's draw for the case of the water. The Prandtl number is around 2 to 6. So for the case of the water, the kinematic viscosity is more, hydrodynamic boundary layer will be more, and the thermal boundary layer will be less. Simple. And one more thing we have to keep in mind that for liquid metals like mercury have very low Prandtl number, very low Prandtl number. It means that thermal diffusivity is more. That means thermal boundary layer will be very thick. Since their K value is very high, thermal conductivity is very high. That's why its thermal diffusivity is more than the kinematic viscosity. Although it is viscous, but it is more conducting. I mean, its conductivity is more dominating. That's why its thermal boundary layer will be more. Lubricating oils like engine oils may have Prandtl number up to 100. Prandtl number means 100 watt. It means kinematic viscosity is more. I mean, oils, we know that oils are very much viscous. So, kinematic viscosity of fluid signifies the momentum diffusion rate through fluid layers, and the thermal diffusivity of fluid defines heat energy diffusion rate through fluid layers. And Prandtl number can compare the relative magnitudes of momentum diffusion rate and heat energy diffusion rate that are occurring through the fluid layers in the respective boundary layer, that is hydrodynamic boundary layer and thermal boundary layer, which are formed simultaneously on the flat plate during convection heat transfer. This is the concept of the Prandtl number. That is very important number and very used in the heat transfer. So in the next session, we'll understand some further interesting topic. Goodbye.